Swayam Prabha. Digital India. Educated India.
So in the last class we had started talking about this idea called radiation impedance. So any acoustic element, when it radiates sound into free air or atmosphere, there is an impedance offered by the larger atmosphere onto that acoustic element. And we had developed analytically a relation for a pulsating sphere, what its radiation impedance would be. We have not developed any analytical relationship for other acoustic elements. Let's say you have a membrane moving back and forth, which is mounted on a flat surface. What is the impedance which that membrane sees as it radiates into free air? We have not developed relations for those types of elements. So what we'll talk today about will be, we'll talk a little bit more about radiation impedance of a pulsating sphere. After that, we will take a detour and we'll talk about a concept called duals, which is relevant in context of radiation impedance particularly, and in general about these electrical mechanical networks. And then we'll go back to radiation impedance and see for other elements, other acoustic elements. So that is what we plan to cover today. So in the last class, we had developed a relation for radiation impedance of a sphere, and the acoustic impedance looked something like ZR, and that was Z naught times SR naught over SR naught plus C. This is for a pulsating sphere. So it's expanding and contracting back and forth uniformly in all directions. And if you remember, impedance in general is essentially pressure over velocity. In context of radiation impedance, we had also talked about per square area and stuff like that. So the question we had posed in the last class was that if I have this impedance in a circuit, in my acoustic circuit, and if I have to break it up into small resistors, capacitors, mass elements, inductors, how will I do that? In other words, if I have a pressure applied here and I have a black box which can constitute a group of different resistive, inductive and capacitive elements, then how will this network look like so that the impedance offered by this network is equal to this? That is what we are trying to figure out, because if we know that, then we can put those resistors, inductors, capacitors in the whole circuit and we can solve. So what you see here is ZR equals Z naught. Z naught is a real constant number, rho naught times C. So ZR equals Z naught times SR0 over SR naught plus C. And so let's see how this ZR behaves. As S goes to 0, S, remember, it's J times omega. So as S goes to 0, ZR approximates to Z naught times SR naught over C. Right. So at low frequencies, the radiation impedance of a pulsating sphere looks like that offered by an inductor, right? Because there's an S term and everything else is constant. So this mimics like an inductor. Inductor in the context that Z equals P over U, right? So I'm in the impedance analogy land. Also, as S goes to infinity, that is, as my frequencies are very large, ZR approximates to Z naught, which is independent of natural frequency. So at higher frequencies, the radiation impedance looks more like a resistance. So we know two things, that if I have to break this into electrical elements, it's composed of an inductor and a resistor. So the only question is whether it's in a parallel or in a series, right? So if it was in a series, the form would look something different. So clearly it's in parallel. So I construct a circuit and I put a value R here, put a value L here, and this is my VV. So if I use the impedance analogy, the value of R would be Z naught and value of L would be Z naught times R naught over C. What is R naught? R naught is the radius of the pulsating sphere. It's a pulsating sphere we are talking about. Remember that. Here R naught is radius of the pulsating sphere. So this is the electrical circuit which mimics the behavior of radiating impedance when a pulsating sphere is pushing sound into larger atmosphere. And just you can double check to cross check. If you put these and you try to compute the overall Z, you will find that that number comes same as what you have developed here. So this is for impedance analogy. So if I move to mobility analogy, then we had talked that my inductors become capacitors, R becomes 1 over R, and so on and so forth. So my mobility analogy will be something like this. So this is R equals 1 over R. This is capacitance. My across variable is VV, through variable is pressure. So you see that. So here C, the value of C is same as value of R, which we had said Z naught times R naught over C. And the value of R is 1 over R. So it is Z naught. I think I made a small correction is due. So here it's actually velocity. So I have to adjust if I have to go to, yeah. So if I use volume velocity and the pressure, then in impedance analogy, my L, which is the inductive part, is basically Z naught R naught over, what is the transformation ratio? A, right? And my resistance is Z naught over A. We see two things here, that when we move from mobility to impedance and impedance to mobility, capacitors. We have seen this earlier also. Capacitors become inductors, inductors become capacitors, R becomes 1 over R, and so on and so forth. But one thing which we did not very explicitly talk about is that if there are some elements which are in parallel, then when we transform it to the other analogy, they come in series. So that is what we are going to talk about now. And that is the context in which we introduce this term called dual. So we will talk about duals. So let's consider a simple circuit. I have a voltage source Vs, which is connected to a bunch of elements, electrical elements. So I have a resistance here R1, another resistance R2, inductor L, capacitor C. The current going here is I1. The current going in this loop is I2. So the current in this loop will be I1 minus I2 in a vectorial sense. So I have one loop here. This is one loop, and this is another loop. So what we do here is, because I have an external voltage source, I'll try to solve this problem using Kirchhoff's voltage conservation laws. So I'll apply that law for loop 1 and I'll apply that law for loop 2. So I will get two equations. I have two variables, I1 and I2, so I can solve for two. So for loop 1, what do I see? So first I move to frequency space by mapping this into their impedances. So C gets mapped as 1 over Cs. L gets mapped as L times S, right? So once I have moved there, then for loop 1 my equation is going to be 1 over C times S times I1. Okay. So that, and then in this part I have R1 times I1 minus I2, and this entire thing equals Vs. And then for loop 2 I have R2 times I2 plus SL times I2 plus. So here I take I2 minus I1 times R1 equals 0. Okay, and now I rearrange this and just construct a simple matrix. So my unknown variables go into a vector. The unknown variables are I1 and I2. On the other side of the equation I have my known variables Vs and 0, and here I have 1 over Cs plus R1 minus R1, and then here you have R1 plus R2 plus S times L. Okay. Look at this matrix equation carefully. So you have this part. What is this physically? It is 1 over Cs plus R1. So it is essentially the overall impedance of first loop, right? This same thing here also. R1 plus R2 plus SL is the overall impedance of the second loop. Okay, and these two terms, this is like a finite element equation, not strictly like a finite element equation. These are coupling coefficients. So minus R1 in the first equation and minus R1 in the second equation is the common impedance, which is common to loop 1 and loop 2. So remember this, because then when we go to another example, you will see very good similarities. So you have constructed a set of equations, and then you can now invert this matrix and solve for I1 and I2. So now we consider another. Here instead of a voltage source, I have a current source, IS. Okay, and the circuit looks something like this. So the value of this inductance is L, this is R1, this is R2, these are resistors, and then I have a capacitor. In this, I have a current source. So instead of using Kirchhoff's voltage potential conservation law, I'll use the other one, current conservation approach. So I have two nodes here, E1. So let's say the potential at node 1 is E1, and this is another node, E2. The potential at this node is E1, potential at the second node is E2. So using conservation of charge, I develop relations. Again, I have two unknowns, E1 and E2. If I know E1 and E2, then I can compute everything. So I have to figure out what is E1 and E2. I know what is IS, L, R1, R2, and C. So the current going coming into node at this first node will be same as current leaving this node. That is essentially what I am trying to do. So my first equation becomes E1 over SL, which is essentially I1, okay, plus E1 minus E2, which is the potential difference across the resistive element R1. So the current going through that will be that whole thing divided by R1. That equals, what will come on the right side? IS. Similarly, the second equation becomes something like this: E2 minus E1 over R1 plus E2 over R2 plus E2 times CS equals 0. Right. So now I rearrange some of these terms, I construct and put them in a matrix form. So my unknowns will go in a vector, E1 and E2. On the right side, I put my known quantities, IS and 0, and my first term in the matrix is 1 over LS E1 plus 1 over R1. Then I have a 1 over R2 negative. Again I get negative 1 over R2. Then I get here 1 over R1 plus 1 over R2 plus C times S. So again we have a matrix of different equations, two equations. So what is the first term in this matrix? It's 1 over Ls plus 1 over R1. Physically, what that means is, it is the total admittance at this node, right? Admittance is like 1 over, yeah,
It's 1 over R1,
1 over R1.
cross diagonal times 1 over R1.
Instead of minus 1 upon R2, it should be minus 1 upon
Yeah. Let me use the eraser. Erase this. Yeah. So this term, let's call this term A. A is the admittance of elements at node 1. Admittance is your 1 over impedance type of a term. Similarly, this term, which corresponds to node 2, is admittance of all the electrical elements which are coming in at node 2. And this term, minus 1 over R1, is the admittance of the term which is common, which connects, physically connects node 1 and node 2. That is one thing. Other thing is, now let's look at the values of these terms. So what you are seeing here is, just let's compare. So you have 1 over Cs plus R1, right? That becomes 1 over Ls plus 1 over R1. Similarly, you have R1 plus R2 plus S times L. Here what you are getting is 1 over R1 plus 1 over R2 plus C times S. So what essentially you are seeing is that the circuits look similar, but they are not identical. The matrix equations look similar, they are not identical. But if you compare these two circuits, the first circuit where we had a voltage source and the other one where we had a current source, then V transforms to I and back and forth, C transforms to L and back and forth, R transforms to 1 over R and back and forth. Right. Series elements which are in series, they go in parallel and vice versa. Elements which are in series, they go in parallel. Elements which are in parallel, they go into series, like R1 and R2, and then you see here. So R1 goes in parallel to R2, and so on and so forth. What else? Yeah, a current source transforms to voltage source and back and forth. And one thing which remains constant in this is power dissipated in the circuit. So power dissipated in circuit does not change. Also power dissipated in every network and across each element, that also does not change. So circuits like the two which we saw, they are called, one is called, circuit A is called dual of circuit and vice versa. Every electrical circuit which is composed of these three types of elements, purely R, L and C, you can have its. Another thing to note is that if I have a matrix of equations only, if I have just the equations, for instance, if I am just looking at this equation and I do not know the circuit, then it's fairly straightforward for me to draw an actual circuit of the whole system. How will I do that? When I look at the circuit, I'll say, oh, there's a current source here. So I'll put a current source. Then I will say it's a 2 by 2 matrix. So there are two potential nodes in the system. So I'll put 2 dots. Then I will say what is the impedance of the 2 nodes which are connected to each other. So I will say that the admittance, when I look at these blue boxes, is 1 over R1. So I connect them by a resistor of value R1. Right. Then I say at node 1 I have 2 elements, an inductor and a resistor, and they are in parallel. So using that kind of a thought process, I can construct a circuit if I just know the equations of the overall system. So if I know the system, I can develop equations. If I know the equations, I can construct the overall network. So we'll very quickly do one example for illustration. Let's say it gives me 7 volts. And this is a purely resistive circuit. So this is 8 ohms. The value of resistance here is 4. Value of resistance here is 2. So the equations. So I have 2 loops. Loop 1. And this is loop 2. Let's say the current going in here is I1 and the current going here is I2. So my equations become 8 plus 4 minus 4 minus 4 4 plus 2 times I1 I2 equals my external voltage is 7 and 0. So this is a DC circuit. So everyone can see the equation. So solving this, I get I1 equals 3/4 of amperes. I2 is half an amp. Given this, can we construct a dual? So my first step will be that I write the equation of dual. So what will go in this vector? V1 and V2, or E1 and E2. Okay. What will go in the on the right side? It will be 7, but this is a current source. 0. What will be the first element of this matrix?
1 by 8 plus 1 by 4.
It is, remember, it's admittance.
1 by 8 plus 1 by 4.
So it's 1, the resistance value will be 1 over 8, but the admittance will be 8. Right? So it will still be 8 plus 4. Do you see this? Here, these elements are impedance values. Admittance is 1 over that. So this is a resistance of 8 ohms, which will transform to a resistance of 1 over 8 ohms in the dual. But the admittance of that 1 over 8 ohms will be 8 ohms, 8. Right. So it will still remain 8. So 8 plus 4 minus 4 minus 4, 4 plus 2. So now we construct a Ranjan, you got it? Yes. So now we construct a circuit for this. So my first thing is that there is a current source, 7 amp current source. How many nodes does this element have? 2 nodes. So first one is at a potential E1, second guy is at a potential E2. What is the element which is connecting E1 and E2?
1 by 4 ohm resistance.
1 over 4 ohm resistance. The other thing is 4 and 2. So 1 over 2. And then on the first node I have 8 and 4, 2 elements. each of impedance 1 over 8 and 1 over 4. So that is my equivalent circuit. So the current here in going through 8 ohm resistance is 3/4 amp. What is the voltage of E1? Voltage at E1. What is the potential at E1? Huh?
7 by 8.
No, E1 will be 3/4 based on, right. E2 is half volts. What is the potential drop across this resistor? 8 ohm. 8 times 3/4, right? How much is that? 6. So voltage drop across 8 ohm resistance is 6 volts. So the question is, how much is current going through 1/8 this resistance? 6 amps. And so on and so on. So let's very quickly find the power dissipated. So in the first circuit, power dissipated will be 8 times 3 over 4, 8 square times 3 over 4 plus 2 square, half square times,
Sir,
yeah,
sir, from the voltage diagram, the voltage source diagram, so it should be 1 over R times.
1 over 1.
So it is 8 plus volt. So in the voltage, when there is a voltage source. And sir, just now we have seen that if the resistance is R1, it becomes 1 by R1 in.
Yes. So we have these.
Okay, resistance.
So yeah, it's a little jumbled up here. So what I'll do is I'll erase this now, so that we can find the power dissipated on this page itself, rather than going back and forth. So power dissipated here in the first circuit is 3 over 4 square times 8 plus half square times 2. And what's the current going through the 4 ohm resistance? What's the value of the current going through 4 ohm? 1/4. So everyone sees that the current going through 4 ohm resistance is quarter amps times 4. So if I do all this correctly, my total heat is 5 or 5.25 watts. Okay. And in the second case, so here my current is 6 amps and here my current is 1 amp. So my total power in this case is 36 times 1 over 8 to the first resistor plus 1 square times 1 over 4 plus 1 square times 1 over 2, and that again comes to 5 1 over 4 watts. So these duals are good to know. Why? Because in your real complex circuit analysis, you may find that, oh, it's easier to move from mobility to impedance or impedance to mobility and so on and so forth. So when you are transforming one model into the other model, some of these laws have to be preserved. So it's just not that capacitors become inductors, R becomes 1 over R, but also series goes into parallel and so on and so forth. So it was for that reason we transformed this particular network. When we moved to mobility model, the R became 1 over R, L became C, but because they were in parallel, they went into series. So that is the context I wanted to introduce, that for very sound engineering reasons, you go from parallel to series and so on and so forth.